Hello, good morning. Uh, Today we are going to cover the chapter 4. Try to mute all. So as I mentioned in the email, we are going to spend one single lecture to go over the discussions in chapter 4. So please read the chapter and try to pay attention to the chapter examples as well. So before that, let's try to recall for the first unit was talking about the energy and their interconversions between heat, work, and internal energy and enthalpy, right? And we try to look at the ideal gases and how the real gas will departure from ideal gas and how do we account for their deviations. But if you think about the unit 4, the exam, the homework and the discussions, we have not talked too much about the mixtures, especially when it comes to the real gas mixtures. So here I'm showing you one single slide to sort of illustrate the idea what we need to understand about mixture on the real conditions. So basically we are still relying on the equations we have talked about, the variable equation of state, the cubic functions firstly proposed by Van der Waal and developed over the years by various other researchers. And then we also have the very nice tool of corresponding state principle, corresponding state series, CST, whether it's 2 parameter for the simple fluids or 3 parameter, thanks to pizza with the idea of eccentric factor. And when we think about the mixtures, whether they are in the pure gas phase or they are in the phase mixtures, say liquid gas equilibrium. So we normally have two energy inputs to manipulate the state of the mixture, normally by this work and heat diagram over here, right? So try to always recall the direction of the energy flow and when we will take the positive or negative sign of the energy values. And then when we think about the heat, we need to revisit a few things, especially when we are going to have the heat. So if I try to have some note over here, so we are going to have the heat input, and the heat will change the state, will change, make a change. Of the system. So when we talk about the change, we could have the following discussions. One is we are staying with the same phase. It's purely the thermal state change, more or less PVT would be changing. The other is, well, we are going to drive the phase change. So there we are going to, for example, we are going to have the vaporization. If we are going to input enough energy to a liquid phase, then we are going to drive this from liquid to vapor or gas phase transformation, right? And if we keep adding energy, then at some point, even for the pure gas phase, we are going to decompose molecules. Too much energy, and the molecules are taking advantage of the energy, and they are going to react with each other. So we are going to have reactions. So this is why in today's lecture, when we talk about the heat effect, try to visit all those 3 different catalogs. Try to look at for those applications, how do we deal with heat. So now let's visit one by one. So first of all, let's try to take a look at the first case, the simple case that I have over here. So when we are going to have the heat transfer to a system and we have the assumption that no phase change, no chemical reaction, and of course no composition change. The number of moles or the type of molecules, they remain as constant. And then it's simply we are going to understand the heat input will change. If I have heat flow in, then very likely the temperature will increase. Otherwise, the temperature will decrease. And then the second term is sort of the quick review on the Gibbs phase rule. Say we are going to have a homogeneous substance with constant composition. So let's say we are going to have pure component 1. So the number of composition would be 1. Number of phase would be, so that would be C minus, no, C minus pi plus 2, right? So if we are looking at the pure substance, that would be 1 minus 1 plus 2, that would be 2. So as long as we understand that two control parameters, then we should understand the state of the system. So that leads to the discussions we have had in the past. Whenever you are interested in a property of a system, and after you've identified the two parameters you are happy with, then we can always write this as a starting equation, right? So now we are interested in the internal energy, and we are happy to monitor the change of temperature and volume, and take a look at the resulting change of the internal energy. Then we can express the internal energy as a function of temperature and volume. Moving forward, we are going to take the four derivatives so we can separate the two independent parameters to look at their respective effect on the system property. So if we move further, trying to look at how we are going to replace those partial derivatives, we talk about the general idea. When we are not very happy for the time being, the partial derivatives, then we typically call this as a coefficient, or we just go ahead and define some other quantities to represent those partial derivatives. Here comes the first case of, now if we take a look at this partial derivative of du over dt, while keeping the volume as a fixed value, then this is the definition of CV, right? So we have du, if you recall, du over dt is related with CV. On the other side, if we are looking at the enthalpy, dH over dt with the fixed pressure, and we'll come to that point why we pick up TV and TP. That is corresponding to the C sub P, right? So we try to simply modify and replace this partial derivative by C sub V, the specific heat capacity. Then we receive this generalized equation, right? So we cannot move any further without the assumptions. So this is why we try to have some discussions using this equation to look at the simplified cases. Basically, we try to focus on the second term, thinking about the when we can get rid of the second term. So for the following three cases, we can treat the second term, and their contribution would be 0. So the first case is for the constant volume. That is for sure. When we are going to have the constant volume, dV would be 0. So the second term would be 0. For the second case, we have this ideal gas. If we have the ideal gas condition, then the energy du will be simply Cv dt, dH would be Cp dt, as we discussed in previous slides. So the second term does not contribute anything to the system. The third term is if we are going to deal with fluids, most likely if we are dealing with liquids or solids, and we can hardly compress those fluids, so then the volume change, the du over dv term would be very close to zero. So we are going to neglect the second term for incompressibility of those liquids and solids. So there you can see that we try to simplify the general equation to receive the equation over here, the last equation on this slide. So there we know this is du is simply Cv dt, then we can try to run the integration on both sides from the initial temperature T1 to the final temperature T2. So that was the general pattern for the discussions. When you're looking at the enthalpy, that's more or less the same story, right? We started with the understanding that enthalpy could be expressed by temperature and pressure. So that would be the choice of two independent parameters. Then we take the full derivative on both sides. We have dH over dt, dH over dP term. And very similarly, we use the definition of specific heat, C sub P, to replace the first partial derivative, and for the second, we try to come up with ideas when we are able to neglect the contribution of the second term. So there again, if we are going to have the constant pressure process where dP would be zero, or when we are going to deal with ideal gas, then it's happy that we are able to get rid of the second term and only focus on the first term. So in those cases, we are having a simplified equation for the enthalpy calculation, and we can, of course, take the integration to understand the change. So those would be the state function. So we can take a look at the initial and final and understand the change of the system. Also, I want to quickly recall that when we introduce and derive the equation, first law of thermal for steady state flow process, we had some discussion about the work, where we are going to have the PV work and the shaft work. So here, that short paragraph was talking about what kind of assumptions we normally do for simplified cases involving steady state flow process. And we understand from those previous discussions that the heat flow for the steady state flow process, Q would be the change of enthalpy of the state. So we are moving from the pulse function to state function. Okay, so those would be the general ideas we've talked about. Now, when you take a look at that equation itself, so here we have this term of Cp, right? The specific heat is defined how much energy I shall need in order to increase the temperature by 1 degree C for unit mass substance. And you may think about that if I'm starting with the unit mass at different temperatures, I may need a different temperature input in order to increase by 1 degree C or 1 Kelvin of the substance. That is really the understanding from our daily life experience that Cp value or Cv value, they are kind of depending on the temperature. So sometimes we could treat those as the constants, but for the general discussion, we should understand the specific heat and its dependence on temperature. So that is why, in general, we need to look at this equation. Okay, so from this T1, T2, say Cp for delta H calculation, dt. For the simplified cases, we can treat this as a constant. So we treat this as a constant. Then we simply multiply this by T2, T1. For more general discussions, that Cp value should be a function of temperature. Okay. And then we cannot just put the Cp, move Cp out of the integration sign, and we have to replace Cp by this temperature function and run our integrations for each of those terms. All right. So this is the first. Yep.
What about for CV? Does CV have?
It's the same story.
Same. Okay.
Same story. So we also have Cv over R. Would be a function of those. You may ask why we have this Cp over R. Why not just go ahead with this simply Cp is A plus Bt plus Ct square plus D term. Well, that was a choice when people were talking about the Cp-Cv dependence on temperature, and especially when they were trying to measure all those coefficients of A, B, C, and D, they find that it's a little bit better to look at the equation itself, especially those coefficients, they are having a multiple factor of R. So that is simply a mathematical choice of expressing the left term as Cp over R, not Cp itself. Right? So that is a side note over there. So when we try to look at those new sort of equations, the first thing come to our mind is let's take a look at the unit. So this is why I want to quickly look at the unit analysis, especially when you are looking at this A term. A is not depending on temperature. A is just a constant, a dimensionless value. So this is why we know that Bt, the product, Ct squared, the product, dt to the power of -2, they shall have the same unit, the dimensionless nature of the A. So altogether, that Cp over R shall be unitless. Okay, so that is basically the message from the highlighted sentence. So then how about those A, B, C, D? So you can see that in thermal, we come up with a concept. We try to set up the equation. Then we try to simplify the equation to have some fun. And then coming to the actual problem solving, then we do need to know the constants involved in those equations. We always need to figure out what would be the A, B, C, D values. For the previous discussion for the...
Hey, Professor.
Yep.
Your connection cut it out. Can you go like a minute back?
Okay. So I was trying to talk about that in thermal. We always have the philosophy. We come up with the idea. Then we derive the equation. For the generalized equation, we try to simplify, trying to get rid of a few terms so that we can have application for specific cases. And then even for those simplified equations, very likely we are going to use those coefficients. For the equation 4.4, we need to have the ABCD value, right? Uh-oh. Are we still here?
Yeah, I can still hear you.
But my iPad disconnected. Yeah,
I think it's back or
now it's back. So for here, we need to know the ABCD coefficients. And back to the previous discussions, we need to know the BCD for variable. We need to know A and B for Vandois or cubic. And we try to correlate those with TC, PC, and VC, so on. So there is always a need of correlating or running experiments and figure out those constants. So this is why we need to have access to those appendix. When you check the appendix of the textbook, those constants for some popular solids and liquids, those values, ABCD values for specific heat, those values are provided, measured by others and available to us in the appendix. Okay. So that is the first discussion on CP and CV. So CP and CV are a function of temperature, Okay. So once we get to that point, then you can see that we try to repeat the following discussion with the same sort of pattern. So there we try to look at the ideal gas once we understand the CP/CV value. So on this slide, I did not derive, but go ahead and tell you some information. Previously, from last lecture, we know that for ideal gas, we know that Cp minus Cv would be R. Okay. Try to visit the previous lecture and appreciate how we derive that equation. So over here, we try to further introduce the correlation. Even for the ideal gas, we know their difference should be always R, but what about their specific Cp and Cv values? So we know that for monatomic ideal gas, we are going to have, say, argon, right? We are going to have the Cv value would be 1.5 R, and the Cp is, of course, Cp is always Cv plus R for ideal gas. And then for the diatomic gases, say nitrogen and oxygen, that would be Cv is 2.5 R, and Cp is basically Cv plus R. All right. For more complex molecules, then it's a little bit harder to have this really neat and exact value. Say if I have ammonia, if I have water, then we cannot have this very nice correlation. So CV and CP is a little bit more complicated because we are going to correlate more intermolecular interactions from advanced thermal. So it's not easy to derive the very clean expression for CV and CP. Despite that difficulty, if we are able to treat ammonia and water as ideal gas, that equation will be valid always for ideal gas. Okay, So that is the first discussion we could have for the ideal gas. How about the non-ideal? If we are moving from ideal to non-ideal, well then just look it up for those coefficients. Okay, and try to see what would be their exact Cp and Cv values. So that is basically the message on this slide. So if we have a problem of relatively medium or lower temperature, relatively medium or high pressure, where the ideal gas assumption will fail, then we treat those as real gas or non-ideal gas. Then if you need to run any calculation of Cp and Cv, we have to figure that out independently, and no longer we could have Cp as Cv plus R. So that is not correct for real gas. Okay. How about mixtures? This is the first time in our thermal we start to look at mixtures. So for the heat capacity for mixtures, of course, it would be easier for us to understand the ideal gas mixtures. So for ideal gas, we understand that we don't have any molecular size, so we don't need to worry about the actual size of those molecules because they are having infinite volume to occupy. So we ignore the size of each molecule, and they don't interact with each other. So when you are having a mixture of argon, say oxygen and CO2 and nitrogen, so each of those molecules, they make more or less the same contribution depending on their molar fraction. So if that is the case, then the Cp or Cv value for mixture is coming from the averaged contribution of each individual compound, right? So this is why for the ideal gas mixtures, we are able to calculate the Cp, Cv for mixtures using their molar fraction. So typically you would do, well, I need to figure out what would be Cp for argon, for example, using those A plus Bt plus Ct squared dt minus 2. Then we also figure out the Cp nitrogen using its corresponding A, B, C, D coefficient and figure out at that temperature what would be the Cp value. And then we just do Y argon multiplied by Cp argon plus the molar fraction of nitrogen plus Cp nitrogen. So that would be the Cp mixture of argon and nitrogen, for example. Okay. There is one other way to deal with the mixing rule, which is instead of calculating the individual Cp, argon, Cp, nitrogen, we try to look at knowing the argon A, B, C, D value, knowing the nitrogen A, B, C, D coefficients. Try to figure out what would be the mixture there, A, B, C, D, right? You can see that we are still using the mixing rule, using their molar fraction, and figure out A mix, B mix, so on. And then after that, we stick with the same empirical correlation, try to figure out what would be the direct equation to deal with the Cp mixture. So both ways shall work to calculate the specific heat of the mixture. Now, once we have those uh, equations and coefficients figured out, then we can run the integration. Okay, so here is a side note. For the homework or for exam problem in this part, try to use software, Excel, spreadsheet, or any math software, say MATLAB, anything to help you quickly run the integration. You probably noticed that in the past old exams, we had those problems during the exam, and I was asking students to calculate those various terms and figure out what would be the heat or the enthalpy change for a system of a pure substance or mixtures. So it was a little bit heavy to calculate those values manually, but now I hope you could take advantage of the softwares for the open book, open note type of exam. So we are not really limited by the those trivial numerical calculations over there. So like we have now, we move from, so we know that the dH would be Cp dt. So there we know that this delta H would be the integration of T1, T2, Cp dt. We try to replace this Cp term. And now Cp is expressed as a function of Cp over R, is A, B, C, D term. So this is why you can see that now we are always expressing this by dividing the gas constant R on both sides, so that we are ready to quickly replace this term. Okay, so that is why now instead of looking at this delta H, we try to look at the enthalpy change over R. So then it's simply we try to plug in the A plus BT plus CT squared plus DT to the minus 2 power, and then when you run the integration over dt, this is why we quickly have those term, and this is coming out of T. T naught is a T initial, then T is a final temperature we are interested in. This is why for the constant, then we are going to have this term. For the BT, for the integration, we are going to have the square term. For the CT square, we are going to have the cubic term. Okay. Try to have a quick review if you are sort of forgetting how to do the integration. And D to the negative 2 would be 1 over 2 term after the integration. Okay. Then here is the tough part. We saw from the previous calculation to use the 3-parameter corresponding state principle, and I warned you over there for the first time of the thermal. Whenever we need to figure out temperature, those problems are always more challenging than others, because usually we need to run those iterations, try to have the initial gas, then try to plug in those values and try to see whether it's making sense or not. So the problem statement here says, if I know the initial and the final temperature, and if of course I know the substance of interest, meaning I know A, B, C, D, those coefficients, then evaluating the enthalpy change is straightforward in a way. We just need to run those integration or using the equation carefully However, if we know what would be the initial temperature, what would be the budget you have for a change, which is the delta H over there, and if we need to know what is the final temperature, then those problems will be a little bit more challenging. We need to run those iterations in order to figure that out. So we'll see in a minute on a second slide to see general procedure. Okay, and also sometimes we also rewrite the term slightly. So this equation over there was simply the reorganize of this equation. We rearrange. A few terms. So that we can have the equation shown over there. What's the meaning of this equation? So if I go a little bit to the next slide, so you can see that we try to define the whole term would be the average of the CP, of course, over the range of T naught T. So that is nothing special but the definition of the term. Okay, so you can see that we try to define, which is indicated by the sign over there. We try to define this would be the averaged CP value over R. And we try to make this equation a little bit easier for us. So if I know the change of T naught to T, and I know what would be the average heat capacity for that temperature change, then I can easily figure that out. The total enthalpy change would be the product of CP average and the temperature range. So now if I reorganize this, then this is delta H over this CP average would be T minus T naught. So the final temperature is expressed then over here in this equation 4.11. So you'll see in a minute why we try to reorganize this. This is purely for the mathematical need for the iterations. So with this and the previous slide, we shall be able to run the iterations. So here comes the procedure. If I have the budget, like I said, delta H, if I know the starting temperature T naught, if I know what would be the substance of interest, meaning I have access to the ABCD values, coefficients, then I run the iteration to figure out what is the final temperature I can have. So over there, we usually need to have the initial guess. So that is the initial guess for the final answer of T. And as we have, you can start with the T naught or a very small change from the initial temperature. Say if this is 300 Kelvin, I could use the 300 Kelvin as my initial guess, or I could use 301 as my initial guess. Once I have this T, the guessed T final and the T naught, then I can put it to the equation of 4.9, which is over there, because I have the ABCD values, coefficients, and I know the exact starting temperature, and I've guessed the potential final temperature. So using this 4.9, I can calculate what would be the averaged CP over that temperature change, right? So if I know that, that is, then we try to put it back into the equation 4.11. So that is known exactly from the statement. That is also provided by the problem statement, our initial budget, overall budget. That is the calculated value just now from the equation 4.9. Then we figure out that is a new temperature, right? We from the initial gas, we calculate this new. And we try to compare the deviation. T new minus T initial. Try to look at what would be the change. If it's very small, then we figure out we had the perfect initial gas, and the gas value should be the answer. If not, then we are going to use the new gas value, trying to put it back to the equation 4.9. So now again, ABCD are known to us. T naught is provided. Now we are going to use the just calculated new T final to run the iteration, right? So we are going to calculate the CP average, and we are going to put it back into equation 4.11. We are going to calculate another T final value and try to compare the change, so on. So we run the
This is
iteration
only,
until we are happy with the deviation.
this is if we're doing it by hand, right?
By hand or by computers, by software.
Okay.
Okay. So we are going to have the problem, homework problem on this to make us comfortable on those type of calculations. All right. So that is a slightly challenging one for the iteration when we are asked to calculate anything about temperature. It's always challenging. So I listed a few examples worth studying by ourselves, but I'm not planning to go over those examples. I figured out that is a sort of delay, but we can revisit those if the class thinks we need to go over those again. Then I'll do that in the after lecture video, or somehow during the office hour, I can make some extra video to go over those examples. But for now, let's have those list of problems and try to take a look at in the chapter 4. All right. So this is the first problem I have. So please do your reading after the lecture. So 4.1 was basically talking about the temperature dependence of the specific heat. Now let's take a look at this latent heat during the phase change. So when we talk about the CPCV, we are interested in moving pure substance to still the same phase, pure substance. Okay, we are talking about the liquid water, and there we are still talking about liquid water. But when you are moving the liquid water to vapor or the superheated steam, then we need to look at this special heat contribution during the phase change. And we call those as the latent heat, right? So there, when we are going to have the phase change, specifically at constant pressure, we are not going to have any temperature change, because all the energy import will be used to drive the phase change, moving molecules closer or far away from each other. So there's no temperature change. And I jump on to this Clapeyron equation, we will derive and talk about the other forms of the Clapeyron or Clausius-Clapeyron equation later on in chapter 6. But here I just want to point out that the latent heat is related with, again, temperature and pressure. So there we can use this equation to calculate if I know the substance of interest, then we know the saturation pressure. We just need to measure the change, the dP of the saturation over dt, and then we shall figure out what would be the enthalpy needed in order to have the phase change. So here the temperature is a phase change temperature. Thinking about water, that would be 100 degrees C, right? How about delta V? The delta V is just the change of new phase of the substance minus the old phase of the substance. So then, of course, if we think about the water as an example, that would be the steam or water vapor for water minus the liquid. Try to check on the steam table in the textbook appendix. We shall have those values available to us at various temperature and pressure. That is one other side note, that is when the pressure is not at 1 atm, of course the phase change temperature shall deviate, right? But still we are going to have access to the corresponding vapor volume, specific vapor volume and specific liquid volume in the appendix. So that is the first equation we can take advantage and use. On the following slide, I was listing those equations provided by the book. So you can see that for the engineering, if we are dealing with one substance for our life, we probably want to come up with some easy, simple equations, especially for that substance. So this is why over the years, people have developed and derived those empirical correlations. And some equations are very easy for us to use. For example, this is one equation we could use for the pure liquid at their normal boiling point. By normal, that applies the ambient condition 1 atm. So if that is the case, then we have this more or less a fixed ratio between the enthalpy change of the boiling with respect to the boiling temperature. We are just missing the 10 multiplied by gas constant. That will be the coefficient. And you can see that we may have other type of equations derived by people for the engineering application. So here comes the other one. There, when we look at their correlation, so this N is still normal boiling point, not high pressure, not purposely a low pressure boiling point, but ambient 1 atm boiling process. Then here we try to correlate this as the reduced temperature. What is the so-called reduced temperature? That is basically TR is T over TC, the critical temperature. Right? N over there is simply to remind us this is normal or around the 1 bar 1 atm. And then we may have the other type of the simplified form. So moving from this equation, we should be able to derive that equation. So basically, if I know the enthalpy requirement for one boiling process at a temperature or a pressure, I shall be easily calculate what would be the enthalpy need for another temperature or pressure by using this empirical correlation. Okay. In the book, we have one other example, 4.4, to demonstrate the use of this empirical correlation. Say we have this 100 degrees C, and we know the corresponding delta H. Now we need to estimate what would be the 300 degrees C latent heat. So there we just put in the temperature, but again try to recall this is a TR. So we still need to look it up, the T over TC. What would be the TC value? Okay. Now let's move to the last case. So recall that for the previous two cases, we are mainly focusing on the regular state change, meaning PVT change or simply temperature increase or decrease. For the case two, we were trying to come up with some ideas to look at the phase change, phase equilibrium. There we need to take a look at the latent heat, and we have some empirical equations to look at those heat. Now we need to look at the reaction. So in order to have the discussion of the reaction, we need to also specify the reference. Here we call this as a standard state. So I want to mention that this is a very important slide. Super duper 5-star importance in terms of the concept.
Professor, we lost like 15 seconds, at least me and some other guys.
Hello.
Hey.
Yeah, I'm back. It's a nice reminder that we need to take a quick break. All right. So
You said a quick break?
are we here on the slide?
Yeah, the standard heat of reaction.
Okay. Very good. How about the connection now?
It works better.
Okay.
Yeah.
Great. Looks like the internet always tries to remind us after every more or less 1 hour, we need to have 1 minute of technical issue, the forced break. So, how's the connection? Are you able to hear me and see the slide?
Yes.
Okay, good. Let's move forward. So on this slide, I labeled this as a 5-star important slide simply for the concept. So here on this slide, I was showing you the accepted definition of standard state. What do we mean by standard state? Standard state is purely a reference state. This is because in thermal, in the experiments, we've done lots of measurements for all sorts of thermal properties, but apparently we cannot measure all the temperature pressure range for those measurements. So we come up to the understanding that whenever we talk about a change, let's try to refer to some agreed standard reference or standard state. So this is why we need to understand then what is the definition of the standard state. So on this slide, I have the definition shown in blue over here. So for the gases, we are, so that will include pure and mixture. Then we always go back to the pure substance in the ideal gas state at 1 bar. Okay, so for one example, if I have air, which is recognized as a mixture of oxygen and nitrogen, if I'm going to deal with that air at say 100 bar, say 400 Kelvin, that is not the easy range of ideal gas, right? So now if I need to somehow study the property of the oxygen, then I need to quickly recall the oxygen standard state would be the oxygen ideal gas at 1 bar. And we'll see later what is the meaning and what is the convenience of having this understanding by the example, by the homework. Are you guys able to hear me or see the slide?
Yeah.
Okay, thanks. So that is one example. Whenever you try to look at the oxygen, you try to look at, okay, I need to add the pure oxygen substance. And we need to treat this as ideal gas at 1 bar. So you can see that we need to have the 3 kind of keywords. One is we need to look at the pure substance. We need to assume the ideal gas behavior. And we need to specify this is actually at 1 bar. How about temperature? We don't mention anything about temperature. Temperature could be any temperature as long as we satisfy the assumption of ideal gas and we specify this is 1 bar. This is the so-called normal condition, right? For the liquid and solids, we don't have the ideal gas assumption, but we still need to specify this is the pure substance. Even we are looking at water and ethanol liquid mixture. So for the ethanol, out of the mixture phase, the corresponding standard state would be pure ethanol at 1 bar. Okay, so we try to emphasize this 1 bar, but we are going to allow the temperature variation. So that is a slide of abstract concept, but try to visit this slide when you are working on the homework problem, and you should quickly realize the use of those concepts after the homework practice. So this is number 1, the standard state. So now stop moving forward. Whenever we talk about the reaction, whenever we talk about heat of formation, we always try to take the standard keywords with our discussions. Okay. Number 2, when we talk about the reactions, we need to identify the reactants and the products, as well as the stoichiometry coefficients. When we talk about the stoichiometry coefficients, we are talking about those values in front of in the reaction. Say if I have methane, I'm going to burn that to prepare my lunch, right? This is the equation. Then I need to balance this equation by the coefficients. So carbon balance hydrogen. Now I have this. So the coefficient of methane is 1, oxygen is 2, CO2 and water would be 1 and 2 over there. And we need to also distinguish the sign. For the reactants would be negative. For the products would be positive. I think I had those on the next slide, but anyway. So on this specific slide, we are talking about the standard heat of reaction. So that is one other case we need to emphasize, that is expressed by the enthalpy change. Okay, so we so far we have two cases. One is steady state flow process. We need to use H or delta H change. Here, if we are having reactions, we need to use delta H. It's not the internal energy change. I'll save some remarks for later discussion why we are going to use the enthalpy change to understand the standard heat of reaction in a following chapter. So we'll come back on this later. So one other note to prepare the discussion is we need to always look at those at the same reference temperature, right? So in the standard state definition, we did not specify what would be the temperature you need to satisfy. The answer is no, we don't have any limitation on the temperature. But in reality, when you talk about those energy requirement for reactions, when you try to compare the property of reactants and products, you always want to stay at the same reference temperature. You cannot talk about the reactants at a lower temperature and then the products at a higher temperature, and you try to have the enthalpy difference as the change of the reaction. So here, when you pay some attention to the note over there, so we always have some standard states, but we also need to add what is the temperature of that standard state. So standard state basically implies this is 1 bar, right? But we need to add the temperature information by ourselves. This is the third piece of information. Also, I want to point you to this note. We have this delta H T. Okay, so over here, that is the imply our standard state. That is the temperature of interest. We will have some interesting note is, okay. So for this type of notation, the upper is still standard state. The lower is just 0, is initial. Okay. So moving to, this is where I was talking about the stoichiometry coefficients. So for the reactants would be negative for the products would be positive. Whenever you calculate the energy contributions, you need to multiply this by their corresponding coefficient. So let's take a look at the standard heat of formation. You may ask why, you started the discussion of standard heat of reaction, then you try to talk about the standard heat of formation. What's the point? If we stick with that equation, okay, let's try to use this reaction as an example. Here we need to understand the change of energy involving nitrogen, hydrogen, and ammonia. So when we try to look at the reaction, that H of R, that is a reaction, and we can specify the discussion was confined at the standard state. Then we try to correlate that should be some property of the ammonia, some property of the hydrogen, some property of the nitrogen, would be that kind of function, right? And it was defined that we need to understand those formation. F means formation. If the discussion is at the standard state, we need to take a look at the temperature, because temperature and standard state would be two independent parameters. We need to provide both. Then we need to understand the formation energy of ammonia, hydrogen, and nitrogen. How do we calculate their formation energy so that we can use those formation energy to figure out the enthalpy change of the reaction? So we have two levels of calculations we need to figure out. The first is indeed the heat of formation we need to worry about. So heat of the formation, as I have on this slide, is defined as the reaction that forms a single compound from its constituent elements. Okay, so what if I'm looking at the constituent elements themselves? So oxygen, nitrogen, argon, those would be zero for the heat of formation. This is number one note on this slide. The second is, again, we need to visit appendix in table 4. A reminder, we shall visit two different types of appendix in this chapter. One is the appendix with the specific heat coefficient, A, B, C, D values. The second is we need to look for the standard heat of formation. Okay, many compounds. So if I have ammonia, you look it up. If I have CO2, you need to look it up. If you have oxygen, then this is zero. Okay. And we don't have the unlimited list of those measurements. So those would be usually measured at 25 degrees C. That will lead to another problem later on in this lecture. So you can see that now if we try to look at the standard heat of reaction, so that is the standard sign, that is R is for the reaction, and that is the indication of the 25 degrees C, where those values are coming from for the appendix. And that is the working equation. You need to keep the stoichiometry values, negative for reactants, positive for the products. Okay. So if we try to look at the ammonia as the example, hydrogen, nitrogen react to produce ammonia, then from the definition, that would be reaction Kelvin. This is the standard state. That would be the 2 multiplied by the formation energy of ammonia, right? Standard state minus, because those would be reactants, 3 delta HF formation. This is ammonia. Nitrogen minus 1 delta HF standard state 209 K of hydrogen. So that would be 0. That would be 0 because they themselves are the pure constitute elements. Okay, that is from the table. Table C4. And of course, we only have the value at this specified temperature, not other temperatures. Okay, so that is the most convenient way to figure out what would be the needed heat in order to drive the reaction. And that is related with the exothermic or endothermic processes we discussed in a previous slide. So here is just a list of the table. You need to pay the attention, especially on the writing. So that is the standard sign with the formation, and we can find this at 298 Kelvin. So there we define the pressure is 1 bar, which is implied by the standard state, and the temperature is defined over here by the table itself. Okay. I don't want to add a note. If you think about the diamond, the formation energy is not 0, meaning diamond is not the most stable phase of pure carbon. Okay. So try to visit again the example problem. So here, by now, I've suggested 3 chapter problems for you to review and try to learn from the procedure of those calculations. So here, the first example is at 25 degrees C. So basically, you just need to look up those formation energy, HF, for each component at this temperature, right? And then this would be delta H of the reaction at this temperature for the standard state. That would be the summation of the stoichiometry value of HFI. So that should be straightforward. Just look up the value, and you can see that oxygen and this chlorine would be 0. You just need to look up for water and HCl. Then the question is, what if the reaction is no longer at this 25 degrees C? What if this is at 70 degrees C? So how do we calculate those changes? Then we need to worry about the temperature dependence on this. I probably need to use 3 more minutes to go over a few slides if you stay with me. So here is for the standard heat of reaction at 25 degrees C. That is straightforward. We just look up the appendix, and we have those values. But if we are not having the 25 degrees C, then we need to worry about the temperature effect. So I'm skipping those slides because I've more or less described those terms or those equations in calculating mixtures or reactions. Okay, so let's move on the temperature dependence. So the temperature dependence is the most easily understood by this equation. So we try to have the reaction A and B is going to react, produce C and D. And I know that I need to calculate this delta H of reaction, okay, at standard state, but a different temperature. Let's try to say this is 400 Kelvin, okay? So the calculation goes using the following understanding. Number one, the enthalpy change is a state function. So we are able to design the path without affecting the actual value. So we start with the 25 degrees C. All right. Over there, I have this delta H or 25 degrees C at a standard state, which is the summation of H formation at the same temperature and standard state. Once I figure that out, then I know the actual process is happening at 400 K. So there we try to go from so this is a 400 K reaction. A, B, C, and D. First of all, step one, we try to move from 400 K to 298 Kelvin. Over there, we need to calculate what would be the enthalpy change using the CP equation, right? This is moving from 400 K to 280 Kelvin. This is step one. Step two, now we are at that 25 degrees C. We can calculate there the enthalpy change for the path 2 would be simply the delta H of the standard reaction enthalpy at this 208 Kelvin. Step 3, now we still have to move everything back to 400 Kelvin. So there we again calculate the reactants with products. So that is sort of the remaining reactants together with the products back to, this is 2. Delta H3 would be again the calculation of CP value. Now we are moving this back to 400 Kelvin. Okay, so we try to separate the path at 400 Kelvin by purposely designing the route. We try to look at the pure reactants. What would be the enthalpy change in order to manipulate the temperature? And then at that known 25 degrees C, we calculate the reaction. We assume the reaction will always happen at 25 degrees C. This is because we have access to those values for the heat of formation. And then once we finish the reaction, we may have the pure products. We may have some remaining reactants or partial reactants. And then for that mixture, we are going to bring the system back to the final temperature of interest. Here is 400 Kelvin. So that is a general discussion of the following slides. We will come back next Tuesday to have some examples and go over this sort of designing path. So I hope you can also take a look at the remaining slides, especially on the example problem of 4.6. We will come back directly on this example on next Tuesday. All right, so that's all
Dr.
I want
Paul?
to share. for today.
Will you be posting any kind of solution for the exam so that we can see how to solve those problems if we missed it?
Yes, how can I not post the solution for the exam? So we try to start working on the exam over this weekend, and we'll see if we could finish grading all those copies by next Tuesday. But of course, we will have access to the exam solution, and I'm planning recording a separate Zoom video to go over on my side how I would solve those exam problems.
Okay, that sounds great. Thank you.
Good. Any other question before we leave for the weekend, or not yet?
Are all the